Welcome back to a discussion of the IMO 2020. In this video, we'll cover the Day 2 problems, including a short discussion of the statistics. If you have not checked out the previous video on the Day 1 problems, I've put a link in the description below. Let us begin with problem 4. The problem statement is quite long, but as we go through the problem statement, I will also set up how we intend to solve the problem. So there are n square stations on the slope of a hill or at different altitudes. So for this problem, I'm going to let the stations be vertices of a graph. There are two cable car companies, A and B, each operating K cable cars. So I'm going to draw two graphs, one for company A and one for B. And the way I'm going to do this is I'm going to use an edge to represent a cable car. So each cable car provides a transfer from one of the stations to a higher one. So the edge will always point from lower to higher number, but I'm not going to put that into the graph. The K cable cars of A have K different starting points and K different finishing points. Okay, so keep that in mind. And a cable car which starts higher also finishes higher. So in this case, if we have a cable car from 1 to 4, you cannot have a cable car from 2 to 3. But for example, it's possible to have a cable car from 3 to 5. The same conditions hold for B. We say that two stations are linked by a company if one can start from a lower station and reach a higher one by using one or more cars of that company. So for example, I put in all the cable cars for A in this graph. So in this particular example, 1 and 7 are linked because it can go from 1 to 4 to 7. So we're supposed to determine the smallest positive integer k for which one can guarantee that there are two stations that are linked by both companies. Okay, so as I've hinted, we are going to use a graph approach to solve this problem. So let's take a look at this is the graph for A. And one of the first things you might guess is that actually the graph for under each company, the graph will be a disjoint union of paths. Because this is an important observation, you might want to prove this observation, for example, by doing induction on the number of edges. So for example, at the start when there are no cable cars, the graph is just a disjoint collection of vertices, so that's true. And then when you are adding cable cars successively for the inductive step, the cable car, because they have different starting points, this means that the newly added cable car, right, it must be starting at the tail end of a current path, and because they have different finishing points, the cable car that is being added, it must finish at the head end of a starting path of a current path. So what the new cable car will do is it will join up two paths to form a longer path. So in this way, you have proved that the graph will always be a disjoint union of paths. So with this important observation, there are two further observations. Firstly, two stations are linked if and only if they belong to the same connected component. Secondly, if there are k cable cars if and only if there are n squared minus k connected components. So this follows directly from graph theory. So let us see what happens if k is equals to n squared minus n, or in other words, there are n connected components. Then in this case, we are actually able to avoid the situation required by the question by the following construction. First, let's say this is the graph for A. First, we have the cable cars as follows. And for the graph for B, we have it in the vertical direction as follows. So putting them together, you see that actually for each of the connected components under A, they are of size n, and each of the n vertices in the connected component, they belong to different connected components under B. So this is a construction that you can generalize for in general n square stations, and you will be able to avoid having the requirement needed by the question. On the other hand, once we have k being 1 larger, in other words n minus 1 connected components, then we will not be able to avoid the condition required by the question, because, well, by pigeonhole principle, there will be at least one connected component under A having greater than or equal to n vertices. And because when we move to B, there is going to continue to be n minus 1 connected components only. All these vertices, right, they cannot belong to different connected components under B. There must be some two vertices in that connected component that continue to be the same connected component under B. So in this case, we can guarantee that there will always be two stations that are in the same connected component, whether under A or under B. Therefore, the answer is n squared minus n plus 1 as required. So that's all for problem 4. I will give a discussion of share my thoughts at the end of this video. Okay, let us now look at question 5. So we have a deck of n cards and a positive integer is written on each card. And we have the property that the arithmetic mean of the numbers on each pair of cards is also the geometric mean of numbers on some collection of cards, for which n does it follow that the numbers on the cards are all equal. So for this problem, what we will do is we will actually prove that for every n, it is necessary for the numbers on the cards to be all equal. And the way we prove this is to prove by contradiction. So assume on the contrary that we can somehow find n cards satisfying the required condition, but when not all numbers are equal. Now for purposes of having some notation, I'm going to let A1 to AN be the numbers of the cards arranged in non-decreasing order. But more importantly, I'm going to be ignoring multiplicity and let Z1 to Zk be the distinct numbers among these cards arranged in increasing order. So for example, if the cards are 1, 1, 2, 5, then I will have 1, 2, 5 being the distinct numbers. Okay, and the key step here is to consider what happens if a prime p divides the largest number. Let us consider the arithmetic mean between the largest number and the second largest number. Here is an illustrative diagram with the largest number, second largest number, and the arithmetic mean. So this arithmetic mean is supposed to be the geometric mean of some collection of cards. Well, is it possible to only throw in cards to the left of the cross, but somehow end up with a geometric mean being equal to the cross? No, you minimally need to throw in some cards to the right of the cross, which means that Zk must be included in this collection. So that means that the prime p actually also divides the geometric mean here. With p dividing Zk and the geometric mean, we conclude that p also divides the second largest number. And now we look at the arithmetic mean between the second largest number and the third largest number. Here's an illustrative diagram with the second largest number, third largest number, and the arithmetic mean. Again, this is supposed to be equal to the geometric mean of some cards, but we cannot just throw in cards to the left of the cross and expect the geometric mean to be the cross. We need to throw in some cards to the right as well. This means that the geometric mean must include Zk and or Zk minus 1. Since p, we just showed that p divides both of these numbers, p must divide the geometric mean. Therefore, again, we conclude that p must divide the third largest number. So by proceeding with this reasoning inductively, you can conclude that if prime p divides the largest number, then p must divide every card. Now, when p divides every card, what we can do is we can take all the cards, the numbers on the cards, and divide across by p. Now we have a new deck. The new deck will still have not all numbers being equal, but more importantly, the new deck will still satisfy the required condition of the problem. And the reason is we can write out all the old equations under the old deck with the arithmetic mean equals geometric mean, and then we divide both sides of the equation by p, and we end up with the equations that we can use for the new deck. Therefore, so long as the largest number is bigger than 1, we can always find a prime that divides it, conclude that the prime divides all the numbers in the card, and divide all the number in the card by the prime p. Keep repeating this argument and until the largest number is equal to 1. However, this is a contradiction because not all numbers in the deck are equal, and if the largest number is 1, there are no possibilities left for the remaining numbers. So that's all for problem 5. I will share my thoughts on this problem at the end of this video. And now we are on to the most exciting problem, which is problem 6. So the statement might seem a little confusing, but I'll help to clarify it. Prove that there exists a positive constant c such that the following holds. Consider an integer n and a set of n points in the plane such that the distance between any two different points is at least 1. Then show that there is a line L separating the points such that the distance from any point to L is at least c times n to the minus 1/3. Okay, so there are a lot of such that in this problem, which makes it a little difficult to understand. So I will introduce some terms and try and rephrase the problem. Firstly, if I'm given a certain configuration of points and I'm given a line, I'm going to define the mean point to line distance to be the minimum distance from any point to the given line. So in this diagram, for example, the mean point to line distance will be this distance here. Okay, and now I'm going to consider all possible ways to place a line, and I'm going to call optimal line to be the line that maximizes this mean point to line distance. So in this diagram, I roughly try and guess this is probably where the optimal line would be. And what the question is saying is we want to show that there exists c such that I find I look at the optimal line, and the mean point to optimal line distance is always at least c times n to the minus 1/3, no matter the n and no matter how the points are arranged. Okay, now I want to discuss a little bit about how you might try to find an optimal line for the configuration of points, which will give a further insight into how we will want to approach this problem. So let's say you have the points here and you're looking only at vertical lines for now. Where would be the optimal place to slot the vertical line? Well, what you would want to do is you want to first project the points onto some horizontal direction, and then look at the gaps here, the adjacent gaps, and see which gap has the largest length. So for example, the largest gap might be here, and this will be the optimal place to slot in the vertical line, because then the mean point to line distance will be half of this gap. If you slot at a smaller gap, then the mean point to line distance will be even smaller. Okay, so this is where you might optimally put the vertical line, but of course we are not constrained to vertical line. We can consider lines in different directions. So this leads to the idea of considering gaps in different orientation. So I'm going to define a gap to be the distance between two adjacent feet of projection. So here we have a gap, here we have another gap, a third gap, and a fourth gap. But of course, I can project to a different direction. I have different collection of gaps. And I'm going to let delta be the maximum gap across all orientations. By what we just argued, this is going to be twice the minimum point to optimal line distance. Therefore, it suffices to equivalently show that there exists a constant such that delta is always at least a times n to the minus 1/3. In this way, we have reformulated the problem in terms of looking at gaps. Okay, I'm going to put what we just discussed here because this is what matters to us. Look at the maximum gap across all orientation, find a constant such that the delta is at least this. Okay, now we can approach the problem proper. What we're going to do is we are going to consider two points that are furthest apart. I will call them A and B. Say the distance is r, they are distance r apart. So the first observation is that all the other points, right, they are inside a circle of radius r centered at A. They are also inside a circle of radius r centered at B. This means that all the remaining points are inside this part of the diagram shown here. Furthermore, we can project all the other points to the direction given by AB. And when we project them, the gaps by definition, they are all less than or equal to delta. This means that the distance r, which is the length of AB here, is less than or equal to n minus 1 delta because there are n minus 1 gaps. This is less than n delta. Okay, and now we are going to do a step that is not quite obvious. That is, we are going to consider a vertical line that is located at a distance half away from A. So this line I'm going to call it xy. And we are going to bound the length of xy above and below. And this will give us another inequality on delta. Okay, so for the upper bound, what we're going to do is we're going to look at this right angle triangle. So this is the feet here is length r minus half, the hypotenuse is length r. So by applying the Pythagoras theorem, we have xy being given by this expression, which simplifies this. And we plug in the earlier inequality to get xy being bounded above by this. And in terms of the lower bound for xy, the intuitive idea is as follows. This tiny area here, right, actually contains a lot of points of S. How many? We'll go into that in a second. And for these points to be still a distance 1 apart from each other, because they are squished very closely horizontally, they must be quite spread out vertically, and this gives a lower bound to the length of xy. Okay, here are the details. Now, because if you look at all the projection of the points in S, right, the gaps between them are less than or equal to delta, and this whole length here is a half. It must be the case that there are at least a half divided by delta number of points inside this area. And as I said, all these points, they are inside here, they are squished close to each other horizontally. If you look at the projections onto the vertical direction, look at the gap. So when we have a gap, right, it's between 2 points that are being squashed here. Those 2 points need to be still a distance 1 apart from each other. Since they are squished to horizontally within a distance of half, for them to be at distance 1 apart from each other, the vertical separation between them must be at least √3/2. And because we have this number of points between any two adjacent projections, they must be at least √3/2 apart. We conclude that xy must be at least √3/2 times 1/2 delta, yielding √3/4 delta. Now we combine with the previous inequality, we have xy bounded below and above as required. And we can rearrange the terms to conclude that delta is greater than a times n to the minus 1/3, where a is some constant that you can figure out from here. So this is quite a long problem 6, but I will share my thoughts on what I think about this problem at the end of this video. Okay, so right now let us look at the statistics for day 2 problems. For problem 4, we see that it is not too much easier or harder than previous years. But actually, I think the reason why this is a problem 4 is because the moment you try and figure out what the question is saying, it is quite natural for you to end up with a diagram that is basically something of this form. And from there, you are naturally led down to the path of considering a graph. The key step will then be to take note that the graph actually consists of disjoint union of paths, which will then give you the required solution. I think the biggest hint is to think about what happens, why is it the case that they give n squared as the number of stations instead of some other integers. And that might lead you to naturally consider setting up n different connected components, each of length n, and realize that in that case we can actually avoid the situation required by the problem. For problem 5, 2019 problem 5 was a bit of an exception, but I would say that in terms of the score, it is not too different from previous years. However, my personal opinion is that problem 5 is actually quite a bit easier than previous years, excluding 2019. So why did I say that? When I first tried the problem, it didn't take me too long to consider what happens if I consider the arithmetic mean between the largest and second largest number. Because that's where I try to construct a scenario where the numbers are not all equal. It seems that the largest two will give a problem, and indeed, because I realized that to achieve this as the geometric mean of some cards, I'll have to throw in the largest card no matter what. And that led me to realize that if some prime divides the largest number, then it must divide the geometric mean and therefore divide the second largest number, and then therefore it's quite natural after that to consider doing induction on that idea. So they're ending up with the fact that the prime divides every card, and from there is not too long before the solution is derived. So personally, I think problem 5 is actually one of the more manageable ones in the past. Not sure if everyone will have the same view. But problem 6 is certainly quite a difficult one this year. I think it's difficult for a few reasons. Firstly, the problem is phrased in a rather unconventional way, because you have to consider like the asymptotics of like how this number behaves with n, and it's quite an abstract problem. And also, I think the whole idea of looking at this line xy is a bit of a jump, and it's not easy to come up with this idea. I think what I suspect is something that's more plausible is actually once you reach this inequality here, one of the natural things to realize after that is that we can actually show that n is less than or equal to some constant times r squared. And the reason why this is quite natural to realize is because we have all the endpoints inside this area here. If you put a circle of radius half around each point, right, the end circles will not intersect each other, but at the same time the end circles must be contained within some slightly fattened area of the lens here, because all the points are contained in the lens, right? So when you expand of a radius half around each point, they must be contained in some slightly fatter lens, and this slightly fatter lens scales on the order of r squared, and you can put together all the constants you need and show that n is at most some constant times r squared. So your square root n is at most some constant times r, and you can rearrange and get delta is at least some constant times n to the minus half. So instead of minus 1/3, you can show minus half slightly more reasonably, and this might be one possible reason for the partial credit 1 point. I'm not too sure, but certainly coming up with the n to the minus 1/3 is quite difficult. So that is all for this video. Do stay tuned to this channel for more mathematics video, and hope to see you soon.